Hello and welcome to the second part of Lesson 4. In the previous part of this lesson, we examined how viscoelasticity could impact a simple polymer processing operation. Now I'm going to give an overview of some techniques that can be used to characterise the viscoelastic fingerprint of a material so that its viscoelastic response can be better understood. You should already be familiar with some of the techniques that I'll be discussing and with the terminology that I'll be using. If it's unfamiliar, I'll be giving links to the videos from EPD650 that explain the concepts in more depth. What I would like to do in this part of this lesson is to describe some additional experimental methods that might be useful for you. But let's start by introducing the industry standard way of characterising the behaviour of a molten polymer. And so when you get a polymer batch in, very often what you'll find is a statement of the melt flow index, the MFI, or an analogous kind of measurement. Now, the melt flow index is defined as the mass of polymer that flows through a prescribed die in 10 minutes at a specific temperature and pressure. So it is in effect a kind of controlled extrusion experiment that results in the number that is the melt flow index. Now let's think about this in a little more depth. What we're doing here is flowing a polymer through a die in a given time and collecting that mass. So we are effectively putting a certain pressure on a polymer to generate a volumetric flow rate. And then that volumetric flow rate derives a flow, and we go and measure the mass of material that has been subject to that flow. So what we're doing is we're applying a stress to the polymer and getting a flow, which means that what we're doing is putting ourselves somewhere on this shear thinning curve. So, for example, the stress that we impart on the polymer by means of pressuring it might give a velocity field that gives the shear rate that I've indicated with that blue dashed arrow there. And then the amount of material that will flow will depend on the shear viscosity of the material. And we can see that if we put more pressure on, the shear field will be higher, the material will shear thin more and we'll get more material. Likewise, if we put less pressure on the material, it won't shear thin as much. We may end up in the plateau region and we'll get less material. Okay, so really the melt flow index is just a measure of shear viscosity at one shear rate. It doesn't give us any information about viscoelasticity, or more broadly, any information about the nature of that shear thinning curve. And so, for the same melt flow index, you can get many different levels of viscoelasticity and many shapes of shear thinning curve. So, what people used to find in the past was that for a given melt flow index that's the same across four polymers, two polymers might process very, very well, one might process sort of all right, and the other wouldn't process at all. But they all had the same melt flow index, because the melt flow index is only giving you a very small part of the picture of the polymeric behaviour. So what we really need to do is to have enough data, especially if we're doing quality control between polymer batches, to ensure that we've got a fingerprint of what a good polymer looks like. So let's think about techniques we can use to do that. Now, thinking back to 640, we talked about linear viscoelasticity. When we were talking about linear viscoelasticity, I introduced two key parameters, the elastic modulus and the viscous modulus. We can combine these two parameters together to get a viscosity-like quantity called a complex viscosity. And typically what we did was we looked at the behaviour of these linear viscoelastic parameters as a function of angular frequency in an oscillatory rheometric test. And typically what we found for a polymer melt is something that looks a little bit like the graph I've just put on the board there. This is for a polyethylene, and what we see is that at low angular frequency, G double prime dominates, the orange circles. So at low angular frequency, the material is behaving in a viscous dominant manner. We can see that as we increase angular frequency, those blue dots get closer to those orange dots. Those blue dots are the elastic modulus, and so elasticity starts to play a more and more important role until such a point you actually get a crossover between the two quantities. Here it's at about 70 or 80 radians per second, and we can see that the contribution of elasticity and the contribution of viscosity equal each other. And after that crossover, the material becomes elastic dominant. And so we can get a lot of information by looking at the linear viscoelastic parameters of a polymer melt. Now, stepping outside of this for a second, if there's anything here that I've described that is unfamiliar, please do go and revisit my video on linear viscoelasticity from the rheology course, and the link's there, and I'll put the link in the description and show notes at the bottom of this video. So we know that there's more than linear viscoelasticity. We specifically do our experiments to characterize linear viscoelasticity at a strain that we know is in the linear viscoelastic region, because typically we strain sweep a polymer, we look for the linear viscoelastic region, and then we do a frequency sweep in that linear region to gain our linear viscoelastic parameters. However, of course, polymers have nonlinear viscoelastic regions as well, and it's very useful to know that behaviour. And of course, the nonlinear viscoelastic response is classically seen in the viscosity response or the normal stress differences. And so if you recall our discussions when we were talking about how do we model viscoelastic fluids, a simple linear viscoelastic model predicts a constant viscosity. If we think back to Maxwell, it wasn't until we went to multimode Maxwell with the Wagner damping function, for example, or the Giesecke constitutive equation, non-linear constitutive equations, that we actually recovered a shear thinning type behaviour. So we see the nonlinear viscoelastic response manifesting itself in, for example, shear thinning. Okay, again, if there's anything here that I've talked about that is unfamiliar, please go and view these two videos, all about normal stress coefficients and Giesecke's equation, broadly speaking nonlinear viscoelasticity, such that you're back up to speed. Okay, we also talked quite a lot in 640 about how you measure the rheology of a material. And so I'll put three techniques up that were the core of those discussions, just as a reminder. We talked about capillary rheometry. Basically, it's an extrusion die. We measure the pressure drop across a capillary of known diameter, and we can therefore infer what the rheological response is at that range of shear rates. If we change our volumetric flows and change our capillary diameters, we can perform some corrections such that we can factor out entrance and exit effects and get information typically in the high shear rate region for that material. Now, of course, we could actually put capillary rheometry in line with an extrusion line, couldn't we? We could have, for example, a side stream of polymer taken from that extrusion line through a known geometry with two melt transducers at either end of that geometry, such that we can measure what the pressure drop is across that known geometry and infer one viscosity value for that. So capillary rheometry you might find as some of the online monitoring tools that you can have for processing lines. We also talked about rotational rheometry, a very, very adaptable and diverse technique. We can run rotational rheometers either in steady shear mode, typically we have two plates and one of them is constantly rotating, or we can run them in oscillatory mode. And we talked a lot about oscillatory testing, which was a test that underlies getting those linear viscoelastic parameters that we outlined in a minute or so ago. We also talked in little depth about extensional rheometry. We kind of focused mostly on polymer solutions because the extensional rheometry that we talked about mostly was you extend the material and then you let surface tension take over and watch the capillary thinning that then ensues. We can't really do that for polymer melt, so I'm going to highlight in a few minutes how we might adapt extensional rheometry to measure polymer melts, where the thinning timescales under surface tension would probably be days, and therefore utterly impractical. So again, if any of these techniques are unfamiliar or you've forgotten some of the details about them, please do go and revisit my videos from 640 on capillary, rotational and capillary thinning rheometry. So let's build on these techniques a bit. We talked about the linear viscoelastic parameters being a function of frequency, and if you recall, the way in which we obtained those parameters was by an oscillatory test. An oscillatory test that we specifically targeted to be in the linear viscoelastic region, as I highlighted a few minutes ago. However, we can also highlight oscillatory tests to be in the nonlinear viscoelastic region. Slightly more challenging, but we get some interesting information out of them. So what we have is a contrasting method that gives us information about nonlinear viscoelasticity. If we think about our linear viscoelastic experiments first, I'm going to now call these small angle oscillatory response experiments, because the oscillation angle is indeed small because it's linear strain, and that is where we got our sinusoidal stress response somewhat out of phase with the strain and the strain rate. And so the portion of the stress that's in phase with the strain is the elastic component, and the portion of the stress that's in phase with the strain rate is the viscous component. But typically you will get a sinusoid if you look at the small angle experiments. Now, if we go for the large angle experiments, probing the nonlinear rheometry, what we see is something rather different and something quite interesting. What we see is a non-sinusoidal stress output, and you can decompose that waveform using a Fourier transform approach to get an idea of the harmonic content of that nonlinear stress waveform. And then you can do some analysis on the relative dominance or otherwise of the first, third, fifth, seventh, ninth harmonic of that stress response, and then start to build up some fingerprinting for the nonlinear region in that manner. There's a number of ways in which large angle oscillatory response experiments can be processed, and I'm not going to go into those details here. The aim of this slide is to alert you to the fact that these experiments exist and that they can give a very good characterization of the nonlinear rheology of a material. So we mentioned extensional viscosity. We mentioned extensional viscosity in 640 with specific reference to polymer solutions and capillary thinning, surface tension driven effects. So what we're going to do now is mention extensional viscosity again, but in the context of polymer melts, because measuring the extensional viscosity of polymer melts gives us a great deal of information about the degree of chain branching that we may or may not have within our polymer. Now, we need a slightly different experiment to measure the extensional viscosity of a polymer melt. We haven't got the amount of time to wait for surface tension to do its thing in deforming a polymer. It's going to take a very, very long time. So what we do is we apply a mechanical extensional deformation to polymer. The current commercial devices typically consist of two counter-rotating cylinders with a sample of polymer in between them. When we do rotate those cylinders, what we end up doing is deforming the polymer. And the amount of torque that it takes to rotate those cylinders for a given deformation gives us information about the extensional viscosity. Now, these devices are available, for example, through Anton Paar. They've got a tool called their SER3 tool, the Centmanat Extensional Rheometer Mark III. And these can give incredibly valuable melt data that would be otherwise very hard to obtain. So let's have a look at what some of that data might look like. The plot that I've put on my whiteboard there is extensional viscosity as a function of extension time. So what I'm doing with these cylinders is setting them in motion at a given rotational rate and then measuring the torque and then backing out the extensional viscosity from the torque as a function of time. And so what we'd expect is that over time we're going to be extending our polymer and that we're going to see a change in extensional viscosity. So I've got data here for two different polymers. One is a linear polymer, linear low-density polyethylene, LLDPE, and one a normal low-density polyethylene, LDPE. The solid data points on that graph refer to the Troughton viscosity of both of these materials. Now, if you recall from 640, the Troughton ratio is a ratio between the extensional viscosity to the shear viscosity. And so the Troughton viscosity in this case is saying, well, I know what my shear response is, I know what my deformation is in extension. It's a uniaxial deformation, or I'm going to assume it's a uniaxial deformation. So my extensional viscosity is 3 times my shear viscosity. Fine. Okay. And that's what's plotted there. And so what we're going to overlay onto that are the actually measured extensional viscosities via a tool such as this. So let's see what the linear low-density polyethylene extensional viscosity response looks like. And we can see from those data points there that it actually falls quite close to what we might expect from Troughton's theory. And I've got two different deformation rates of data point there. The plus signs are at 10 revolutions per second, and the stars are at 20 per second. And so we can see that both those deformation rates give us extensional viscosity results that are very, very close to the expected Troughton result. However, for a highly branched molecule, we see something radically different. We see a very, very strong departure from that Troughton result as the material strain hardens. And this is the signature of chain branching that you can pick up with these extensional experiments. So let's look at some cartoon images of what these molecules might look like. Linear low-density polyethylene might have very, very, very tiny chain branches and a very, very long backbone, which means that if you've got a bunch of these things together and extend them, they tend to slip over each other quite well. And that's a kind of idealized sort of response that gives us our Troughton response. However, if we've got low-density polythene, which was the original polythene that was first developed in the 30s, it has significant amounts of chain branching on it. And so imagine we've got a load of low-density polyethylene molecules together. They're going to entangle very, very fast. And the more we try and extend, the more the entanglement becomes, and that is the origin of this extension hardening that we can measure with one of these SER3 tools. The final thing I'd like to talk about is a very elegant technique that allows us to see a stress field in a flow. And this is a very, very brief overview of the subject of rheooptics and stress birefringence. The techniques actually go back a very, very long time. In 1873, James Clerk Maxwell wrote, "In 1866, I made some attempts to ascertain whether the state of strain in a viscous fluid in motion could be detected by its action on polarized light." Now this is very prescient because one of the standard techniques that we use to characterize stress in molten polymer flows today is exactly this. We shine polarized light into the material. The nature of stress on the polymer backbones rotates the plane of polarized light, and we get interference patterns being produced. The sort of experimental setup that's typically used is as follows. You need a light source, preferably a monochromatic light source. So you either go for a high power LED light source that is monochromatic, or you go for a broadband white light source and then put a color filter in place. Typically what we used to use with green color filters at about 540 nanometers. You then have a polarizer, which rotates the plane of polarized light. You have a quarter wave plate, which removes some of the unwanted artifacts. You then pass that light through a polymer melt flow where the melt flow is contained within an apparatus that has quartz glass windows, say. So you can actually get optical access into that flow. Quartz glass windows are de-stressed, and so the stress in the windows doesn't affect the plane of polarization of the light. What you then do is you see what comes out in terms of the light of that flow cell. So you have another quarter wave plate, an analyzer, which is at 90 degrees to the polarizer, and then a camera to record the images. And what you find is that you get these beautiful, beautiful, beautiful patterns. So let me give you an example of these patterns. Let's say my flow cell consists of something that we call a cross slot. We've got two channels at 90 degrees to each other, inflows at opposite sides, and outflows on opposite sides. And so what we have is a shear field and an extension field being generated. If we put a cross slot in between cross polars and look at a birefringent polymer, we see a stress pattern like this. This is for, I believe, a polyethylene, or it might be polystyrene, I forget which. But either way, you get this beautiful visualization of the stress field that ensues. So the first normal stress difference is directly proportional to the number of fringes in this image from the zero stress condition. You've just got to pin down where exactly that zero stress condition is. We can calculate the magnitude of the first normal stress difference using something called the stress optical rule. And the stress optical rule I've put there on the board. It has 4 parameters involved. Script K there is the fringe number you're looking at away from the zero stress condition. Capital lambda there is the wavelength of the light that we're using. Script C is the stress optic coefficient, which changes from polymer to polymer. And script W is the depth of fluid through which the light is travelling. And so if we get an image like so, we can convert the interference fringes effectively into contours of first normal stress difference. Now, Not only does that allow us to visualize the state of stress, but it allows us to do something very, very, very useful indeed, which is see if we can predict the state of stress using computational tools. And so what one can do is use these visualizations of the stress field to compare against calculations of a stress field for a given constitutive equation with a given set of parameters. And depending what the match is or match isn't, we can then see the suitability of either the parameters or indeed the constitutive equation as a whole in order to capture the state of stress of the flow. And there's really no other technique that gives you such a good comparison or a good appraisal of the ability of a constitutive equation to accurately model the state of stress of a polymer. All the other things that we look at, for example, the amount of dye swell or whether there's an instability onset, is as a result of the stress field, but this allows comparison of the stress field itself. So let's summarize a few key points. One of the typical industrial figures that you'll get that gives you information about polymer melt rheology is the melt flow index, but it only tells you a very, very small part of the rheological story for a material. What we'd ideally like to do is to characterize materials a lot better, so in effect we can obtain a viscoelastic fingerprint of a material, and that allows us to do many things, but one of the things that we can do then is apply quantitative quality control of material from batch to batch to batch of different polymer. We can quantify the linear and the nonlinear viscoelastic response of a material in order to get us that fingerprint. We can do that using dynamic flows, and we can use that using steady flows. If we think of the linear viscoelastic response, we've got our two moduli, our viscous and elastic moduli. If we think about our nonlinear response, we've got our parameters such as our shear viscosity. What we can also do is we can use other techniques, for example, large angle oscillatory shear, and then a Fourier transform of the resulting signal to directly quantify additional information given in that nonlinear response. We can use extensional experiments, for example using the SER3, to observe whether or not chain branching is giving us an extension hardening effect in a polymer. And finally, for the more experimental investigations, or the more academically experimental investigations, we can use rheooptical techniques to directly visualize the state of stress in birefringent polymers.